Morning.
Hey, good morning. We'll wait another 2-3 minutes and then we'll start.
I have one question. So in interview, basically, will the questions be on stats and ML, or it would be also for Python codes and all those things?
Yeah, all of them. Interview, you can expect all of them. Code as in? I didn't understand. What do you mean code?
I mean, the commands we write in Jupyter, those things will also be asked, or just a concept
So
in Python?
generally what happens is it depends actually company to company, but most of the times they will of course require you to write some code. So let's say if they're asking you to code, let's say they give you a small task, they'll give you access to internet also, but they'll give you a data set and all that. Sometimes what happens is they give you a data set and then they'll give you like 1-2 days and then they'll ask you to submit the full project. So it depends, like startup, medium-sized company, big companies. Face-to-face interviews will be mainly on concepts, but even in face-to-face interviews, sometimes they'll give you a laptop or they'll ask you to bring your laptop and then write a small program to, let's say, machine learning or anything, a small thing, or could be, let's say, pandas, and then you can use pandas and then do some operations. Coding is must. Definitely they'll ask you.
So total of around 2 to 3 rounds must be possible, right? Minimum.
Yeah.
Mani, I have one question from the yesterday class.
What?
Is I have one doubt from yesterday class.
Okay.
Yeah. So actually, I'm not able to understand what is the difference between strata and cluster.
What is the difference between strata and clusters?
Cluster, yes.
Yeah. So what happens in cluster sampling is, if you see the slides yesterday, right? I've uploaded the slides. So there is one slide. If you see, what they explain is more or less they look similar, but what happens in strata and cluster is, in cluster sampling, you select the whole cluster actually. If you remember the example, so what the
I'm questioning from the slide actually. That is the slide number is 28. Yes.
Okay, what is the doubt?
Some kind of it is said that in the strata the data should be homogeneous, and in the cluster the data should be heterogeneous.
Heterogeneous, yeah.
Yeah, I am not understanding this part.
Okay. So what it means is, so if we, I'm not sharing my screen. If you see my screen, what it technically means is, in cluster, right? What happens is you have cluster number 1, cluster number 2, cluster number 3, and cluster number 4 and 5. So you'll cluster like this, and then you'll select, let's say, cluster 3 or something, right? So this cluster should be heterogeneous within. So heterogeneous meaning, so it should have as much as possible different types of colors, because at the end you select one of these clusters, right? So among these you select one. So what it means in cluster sampling, you have to have within as in like the inside the cluster itself, you should have heterogeneity. Heterogeneity means like difference, like they should be different among each other. So there should be green, blue. If there was red here, then it will be better. So green, blue, red, and yellow. Right. So maximum heterogeneity. Okay. So this is in cluster sampling. Okay. So because you select one of the clusters. Now if you go back to your stratified sampling, what is the concept here? So you basically cleared them into strata. So this is red strata, yellow strata, um, green strata, and blue strata, right? So these are homogeneous. Homogeneous means of same color, right? That is the strategy. So as much as homogeneous, so same color, but you end up selecting one from here, one from here, one from here, and you will end up selecting two from here. So that is the homogeneity within. So within homogeneity here, and you select one of those, each one of those from the strata, and it's the same thing in ulta pulta. Like this is heterogeneity, like within each cluster you have as much as heterogeneity, and select your one full cluster you select. Is it clear now?
Yeah.
Okay. So that is the homogeneity and heterogeneity. It's the same concept in a different approach actually. So sometimes you don't have information so clear that black, red, and green, right? So what you do is you create clusters actually. Forget about colors. If I say you forget about colors, then you create clusters. So like let's say 3 or 4 clusters, but you make sure that whatever the clusters you come up with, let's say you came up with 3, right? So among these 3, which one will you select? So the answer is among these 3, what is the maximum uniqueness or the heterogeneity within it, so that you have a maximum representation. So idea of sampling should be as much as possible you have the representation of your population, right? So let's say there are red, blue, green, and yellow, right? So whatever sampling is you're doing, you have to make sure that as much as representation you can get. So this is a bad sample actually anyhow. So among these, if you can find a good sample. So what if you see here, what they have done is they have created a clusters between 1 to 5, let's say 1 to 4, and like 4 to 8, 5 to 8. So this is a type of clustering, because let's say they don't know what is the color and all that. So blindly you can bucket as, right? So let's say you can bucket them. So when I say there are numbers between 1 to 20, can you find 4 clusters? Yes, many. So of course I will find 1 to 4, 5 to 8, something like that. So these clusters you can find without even any information on what is the color, what is the size and all that. Just you can directly find some clusters, right? So once we discuss clustering and all that, you will understand even better. Okay, but the idea is you should get maximum as much as possible, the real representation of the population. How many more, how many less, any color is more, any color is less, as much as possible. Okay, this is just general theory. If you understand that much, it's, I think, fine in my opinion. Okay, so let's start with normal distribution. So the next topic is normal distribution and central limit theorem. And then if time permits, we can discuss. So can anyone tell me what is a normal distribution? So we'll discuss what is
It is the distribution of data points, means how your data points are distributed. A normal distribution curve, we can see the bell curve, I guess. The name is bell curve, the
Okay.
standard normal distribution. As no skewness will be there.
Okay.
Yeah, it is called standard normal distribution.
Mean mode and median will be same.
Mm-hmm.
It has a non-skew graph.
Okay. No, that's fine. These are all properties actually, right? But okay, let's ask in this way, like, why should I learn about normal distribution?
The other distribution should be compared with the normal distribution.
Okay.
You can see the deviation.
So we can take this as a reference. Okay.
Yeah.
Why only normal distribution? Why not any other, let's say money distribution? I'll come up with money distribution. What's special about normal distribution? And how is it applicable in most of the cases?
In normal distribution, I guess the mean, mode, and median will be same.
Yeah, that is a property, right? Property means when I say this is following normal distribution, I can say that this property. When I say the mean is less, which means, or let's say range is less, that's a property of distribution, right? So it's a property of set of values. What I'm asking is like, why only normal distribution? What's special about normal distribution? So mean median is same. There is 50% symmetrical, 68%. All those are properties. Properties meaning like if I say this is following normal distribution, you can safely assume that okay, this much amount is following that side, this side, all that. So those are all properties. So what I'm asking is why normal distribution and what's the relationship with that's a pretty powerful statement actually. Like why can I use it in most of the places?
Most natural occurring data sets follow normal distribution.
Yeah, so that's the right answer. So in nature, everything follows closely or to some extent, not to some extent, to most of the extent, all the things that follow in nature are normally distributed to some extent, right? So most of the times it is actually very, very clear actually. So I think there are close to 28 people in the class. So if I ask you your age, right? So can you guys think what distribution does it follow? Right, so let's say I'm randomly guessing your guys' age. Let's say there are 28 people. Right, so what is the age? Let's say 27, 30, 22. I think there are young 21. Then there is 25. Let's say 35, 32. Again 32 maybe. Let's say 30. And then again let's say 25. Right, so you can clearly see that this sort of follows normal distribution. Now what is this? This is your age. If I ask you about weight, everyone, like 28 people here, so can you guys tell me your weight? So let's say 70, 55, 60. These are all kg, like 61, 60. Again, let's say some people are not eating food because of corona, so let's say 50. So let's say again 60, 66.5 or something like that. Let's say some people are eating a lot of food during lockdown, let's say 75. Right, again dot. What is this? Again sort of follows normal distribution. So if I ask you again, what about height? What about height of all the 28 people? So let's say 176 centimeters. Let's say there are short people, let's say 170. Let's say there are very tall people also, let's say 180, one guy, let's say medium person, let's say average person, let's say 170. So dot, you get the idea. So any other questions I can ask? Any question I ask, let's say salary. Salary. So let's say every month salary, let's say 40,000. Let's say somebody is in the beginning 30,000. Let's say we have experienced guy, let's say 70,000, 80,000. Let's say we have some people from Google, let's say 85,000. Let's say you have, let's say again basic like 22,000 starting out career. So let's say what is 40,000 again? 28,000. So you get the idea, right? So most of the distributions in nature, right? So these are all 28 people, right? So let's say if I ask you again outside also, let's say if I ask in my office, in my, let's say flat, or let's say in my apartment, or let's say in my lane or anywhere, most of the numbers, right? So that's the beauty of nature, right? So most of them converge to normal distribution into some form actually. Right. So did we discuss any distribution that converges to normal distribution? Did we already discuss something in previous classes which sort of slowly converges to normal distribution?
Mani, I have one question before that one. How the salary comes to a normal distribution? Because one person he is starting from career 0 and he will go to level up to 1, 2, 3, 4, 5 like that. In that case, the salary will also increase like that only, right? How it will decrease again?
No, I'm not saying decrease. I'm saying the person. In this class, there will be a person who just started career, right? So his salary will be 22. Also, there will be a person who has 5 years experience. So let's say he's 45, 50, 60. At the same time,
But if you arrange them in from 1 to some levels, then it will be exponential, right? Not like a normal curve, it will come.
so how many?
How we can say that? How we can say that it will fall under normal distribution? If you say like if we start with career 0 in this class, then it will increase from 1 year, 2 year, 3 year, 4 year like that. It will not come to 0 again, right?
It will not come to 0 again. Now let's take hypothetically 10 values. Okay, so let's take 10 people's salary. So you tell me values. Thinking that class is composed of different types of students. Don't think that there are only experienced. There are like junior developers. There are middle, then there are experienced. Now you tell me some random numbers, 10 numbers you can tell me.
You can go for 1, 2, 3, 4, 5 like that if it is in terms of lakhs.
1, 2, 3, 4, 5. Okay.
Yeah. How it will fall under normally? I'm not getting. Because if we in this class, if there are people with different levels, then we start with level 0 and then we'll go 1, 2, 3, 4, 5 years experience. In that case, accordingly, their salary will also be in increasing order, not in bell curve. Correct.
No, that bell curve is not what you're thinking. So you tell me the salaries, right? So 10 numbers you tell me.
In this, we are not plotting the salary, right? We are plotting the frequency.
Yeah.
And that follows normal distribution.
No, let me clear her doubt. So let me, you tell me, sorry, so what is your name?
Pushpa.
Sorry. Tell some 10 salaries. Keeping in mind.
Maybe, okay, 5 lakh, 10 lakh.
Okay. This is yearly salary, I'm assuming. Okay.
Yes.
Okay.
10 lakh, 15 lakh.
Okay.
20.
Okay.
25.
Okay.
30.
No, all experienced people only you're telling. What about juniors? I'm thinking there are few juniors with 3 years experience or 2 years.
If that is the case, means it should come from before 5. You can mention 2, 3.
Okay, 2 lakhs.
Yeah.
And 3 lakhs.
Yeah.
The 1, 2, 3, 5, close to what? You'll go, I think, with 35 lakhs.
Yeah.
Let's say 40. So normal distribution is not this actually. I mean, like this follows normal distribution. What you're confusing with is the actual values. One thing is you have already sorted. That is, I don't know why you sorted values, but anyhow. So normal distribution is basically the frequency actually. So what it means is the concept of normal distribution is majority of the values. So what is the mean value here? Somewhere here. So the average salary in my class of students is, let's say 18 lakhs or let's say 17 or something. So this is the average, right? So this is the average. And what is the maximum salary I have? 40 lakhs. Okay, 40 is somewhere here. And what is the minimum salary I have? 2 lakhs. Okay. Now what is the majority of the salaries? Majority of the salaries are around mean. What I mean by that is 10 lakhs, 15 lakhs, 20 lakhs, 25 lakhs are around the mean. Right. So let's say this is 15, then this is 10, and this is 20, and this is 25. Right. So how many people are there? All of them are 1, 1, 1, 1, 1, 1. So the frequency is 1, 1, 1, 1, 1, 1 for all of those. So if I plot the frequency, I am not plotting these values. Plotting the values means this. You are confusing with this. This is what? This is basically, let's say individual I1, individual I2. This is not what you are discussing. Individual I2 and I3 and I4. Let's say I3 and I4. This is salary. Let's say salary value per year. Salary value per year. Now this means that you have already sorted money. This is fine. So this is not what I'm sorting actually. What I'm sorting is the number of people actually. So what I mean by that is, this is how it will look like. Somewhat like in your case, this is 40 lakhs, right? So this is, so what it means is majority of the people. So what is, you have to understand your X and Y axis always. So this is your X axis. So this is your salary value per year. And this is frequency. What is frequency? Frequency means that how many people are in this bracket. So let's say this is, what did I tell you? This is 18 lakhs or 17 lakhs. Right? So what I mean by that is majority of the people are in the bracket of majority. What is majority? If I take 6 values, 1, 2, 3, 4, 5, 6. So if I take 6 values are between, so this is one person who has 15 lakh salary. This is 20 lakh salary. And this is 25. Let's say this is 30 lakh salary. Right? So all of these guys are 1, 1, 1, 1. So technically, what I'm trying to explain is, if you take the frequency, right? So if you take the frequency of these buckets, so let's say 1 to 5, 5 to 15, 15 to 20, 20 to 25, and 25 to 30 or 30 to 35. What you have to consider for normal distribution, or saying for bell curve. So this is your bell curve or normal distribution is, money, I see that the majority, so always in the statistics, your reference point will be mean, right? So that is the reason we discussed mean in the beginning. So if you see that, if you see there is an increase and then there is a decrease around your mean. So this is your around your mean reference point. So what you're thinking is your reference point is starting here and it is ending here. So this is not what we are discussing. What we are discussing is the frequency of the people, right? So here frequency is 111. So what it means is most of the people are 60% of the people are around the mean, right? So let's say this is 60% of them. There is a minimum, like the guy who is starting his career. There is a maximum, which is 40 lakhs. The guy who has a lot of experience, 10 years. Right? If you plot the same thing also again with weights, right? There is a person in the class who has a small weight, meaning like less weight, and there will be a person in the class. So majority of the people in the class will fall under average, let's say average weight of the class in my class is, let's say 62 kgs. Okay. So majority of the people, so minimum guy, let's say one person is very, very thin. So let's say he will be 55 kgs here. Right, so majority of the people will be around the mean, right? Let's say this is 60, this is 67, and then some people is like let's say 1, 2 people are, let's say a little bit overweight. So let's say there are 72 and 75. What it means, majority of the people are around the mean, right? So what is your x-axis? X-axis is weight, and y-axis is again, let's say frequency or number of people. You can take frequency. What frequency means? The number of people. Let's say if you take 60 to 65 bucket, how many people are there? Let's say 2 people. So this is 2 people. Let's say around 62 people, how many? Let's say around 62 to 63, how many people are there? Let's say 5 people. From 65 to 67, how many people? Let's say 3 people, right? So how many people are there above 70 to 75? 70 to 72, 1. 75, 1. How about 55 to, let's say 57, 1. Right, so what it means is around the mean, okay, around the mean there is an increase in the beginning, and then the maximum values are around here, around the mean, and then after this part there is a decrease in the number of people, right? So number of people in the weight, right? So this is your weight, this is your salary, and let's say if you take height, right? So there will be generally like this distribution, right? So what it means is the average height of the class. So I have 28 people, 32 now. So these 32 people will have an average height, right? So let's say if I add all of the height and divide, So let's say, what is the average height of a human in Bangalore? Let's say 5 feet 8 inches, or let's say 5 feet 6 inches, right? So let's say 170 centimeters, right? Majority of the people will have, majority means like 60%, 70% will be from, let's say 160 centimeters to 180 centimeters. There are very, very few people, let's say out of 32, 2 people will be, or maybe 3 people, let's say 2 people is 181 centimeter, and one two guys will be a little bit short. So let's say this is 158 centimeters, right? Now what is on the x-axis? X-axis is the height in centimeters, and what is the y-axis? Again, it's the frequency.
Okay. Now it's clear.
Yeah, it's clear for everyone, right? It's a frequency that we're plotting on x and y. So can you guys give an example where this sort of behavior will not be in nature? Can you think of a counter example? I told that most of the processes follow normal distribution, right? So can you think of a situation where this doesn't exist, or this might not be completely true? Any counter examples to normal distribution?
Maybe age of versus weight.
Age versus weight?
Yeah.
No, like generally you say age versus weight. What do you mean by age versus weight? So you're
As the age increases, weight also increases, but later it may not be the true.
okay. So let's say you take the value as age, something like weight divided by age. Okay. I would say okay. Okay, so so that's fine. So let's you guys can think, but most of the things generally follow normal distribution. Okay, I hope you guys got the context right. So what is a normal distribution? Why are we discussing this? What is the use of this? So most of the times in nature, normal distribution is present in some form. So you can always approximate that. So I'll just explain some theory now. So in probability theory, the normal Gaussian, Gauss, or Laplace-Gauss distribution is a very common continuous probability distribution. Okay. Normal distributions are important in statistics and are often used in natural and social sciences to represent real valued random variables whose distributions are not known. A random variable with a Gaussian distribution is said to be normally distributed and a normal derivative. Okay, so this is all theory. So do you guys know central limit theorem? Do you guys discuss central limit theorem?
No, we did not discuss.
Okay, so
This class is we discussed.
okay, anyhow, let me explain. So in central limit theorem, what it explains is, in some situations when independent random variables are added, their properly normalized sum, okay, their properly normalized sum tends towards a normal distribution, aka bell curve. Okay, even if the original variables themselves are not normally distributed. Okay, the theorem is a key concept in probability theory because it applies that probabilistic and statistical methods that work for normal distributions can be applicable to many problems involving other types of distributions. Okay, so this I'm going to explain. So this theory I'm going to explain with the help of a URL. So by the way, this is a good website for learning probability and distribution and all those things. So let's say this is, so what I'm trying to explain here is, so what does CLT, which is central limit theorem, explain? Central limits theorem states that the sample mean of a sufficiently large number of random variables is approximately normally distributed. The larger the sample, the better the approximation. Okay, so let me show you. So let's say, So this is not so normal. Let me do theoretical. Okay. So what is happening here is, so this is your values, right? So these are all your values. So I'm drawing some random values, right? So this can follow any distribution. So this can follow any distribution. So this is following any distribution. So distribution as in, let's say this could be one, as you explained, right? Salary, let's say 1 lakh, 3 lakhs, 5 lakhs, 8 lakhs, 10 lakhs, let's say 12 lakhs, whatever, like, or let's say weight like 176 centimeters, 175 or something like that, right? Any distribution. So let it follow any distribution. So what I'm doing is I'm taking a sample of values. So let's say I take a sample here. Let's say I take a sample here. I take a sample here. How many sample I'm taking? I'm taking 7. So let's say 1, 2, 3. Let's say 4. Let's say 5. Let's say 6 and 7. This is the first time. What is the next step? This next step is sum of, or average actually. So I think it's the sum or average. Both of them should be approximately. So let's say if I take sum of these values. Okay, what is the sum? Let's say I took 1. Let's say I took 8. Let's say I took, let's say again 10, something like that. Now this is first attempt. This is first attempt. Now again I'll come back. I'll take another 7 values from the sample. So let's say I take this one again. So this one again. So let's suddenly I go here. Suddenly I go here. How many? 1, 2, 3, 4, 5, 6. Not here again. Random. It's random. So 7. Again I'll find sum 2 for the red number of sample. Okay. Again I'll come back. Let's say how many draws I am making like this? I am making 19 times draws. Okay, so 19 times I'll come randomly select how many? 7. So let's say this one, and this one, and again this one here. Let's say again this one, random, everything is random, sampling, right? So let's say I'm randomly sampling. Okay. So how many I'm taking? I'm taking a sample of 7. What is my sample size? Sample size is basically 7. How many draws I'm doing? How many draws? Draws are basically I'm doing, let's say 19. Okay, how many doing draws? I'm making 19 draws. Okay, 19 times I'm taking different 7 samples from a continuous values. So this can follow any distribution. What CLT explains, which is central limit theorem, is this summation values are there, right? So 19 times you'll get summation values. Since you're doing 19 draws, you'll get summation 1, you'll get summation 2, okay, you'll get summation 3. Like that, how many you'll get? You'll get summation 19. Right? So what CLT explains is these summation values will always be normally distributed. Okay, so let me prove it. So this is a theorem. So theorem means you generally try to understand and then try to visually understand and use it in your applications. Okay, so we will not prove it with mathematics and all that. So let me do this. Right, so you guys can see, right, so how this is closely becoming more and more normal. So this is your theoretical normal distribution. So you can see here, right, so this particular orange curve is your normally distributed values, right? So this is the normal distribution. So let me clear it again and start from the scratch. I hope you guys are following, right? So what this CLT explains is when you have a sample of values, so when you have any distribution, central limit theorem states that the sample mean of a sufficiently large number. So let's say I do this. So this is decreasing values. So this is, let's say this is sort of weird distribution. So this is original distribution. Okay. What is my sample size? Let me take a sample size, a big one now. So let me take 12 I take. How many draws I'll make? I'll make, let's say 25 draws. Okay. So let's put this out. So that is the summation that is happening. Orange values are summation. So if I put this, sort of, this is not so well. Okay. So let me increase the number of draws to 35 and let me increase the sample size to 50. Right. So what they're trying to explain is, so let me twist this now. So let's say this original distribution is, let's say like this. let's say this is.
So what is that alpha and beta? What is it?
So alpha and beta is just a parameters to tweak this particular yellow color graph. Okay, so even they have not described what it does, but visually what you can understand. So let's say if I go back to 1, and let's say if I go back to 1, right? So this is a straight line, sort of straight line, right? So let's say what is alpha tweaking? So alpha is tweaking like a bump on the left and right, right? So let's say you have increasing values. Okay, let's say is this not going to 1? So what is this? So this is alpha is basically tweaking the bump, actually, like this particular bump, right? This particular bump. And what beta is doing is basically if you increase and decrease the beta, there will be like a sort of a dip, or let's say sometimes up, right? So that is what beta is trying to do. You can forget about this, but what the concept that you have to learn from CLT is, no matter any type of sample you take, okay, it doesn't matter, right? So what it means, CLT theorems proves that this distribution could be anything. It could be like this, it could be like this, it could be like this, it could be like this. But what happens is when you take a sample of, let's say, many samples, how many times? 35 if you take, the summation follows normal distribution. So is this theorem clear? You guys want to try anything else? So let me share this.
Yeah, can we see that if it is less, sample size is very less, it's not a normal distribution. Can you see that?
Yeah, yeah. Yeah, so the theorem also says that sufficiently large number, right? So that is, if your sample size is less, then it might not completely follow or fit a normal distribution. Right? This is not so normal actually. Still okay, but still you can see that sample size, if the sample size, if I go a little bit down also, let's say if I produce this. Now we have a problem because there is a gap here, right? So sort of it's a approximate, so you'll make mistake by assuming normal distribution, but that is completely fine. So that is an acceptable mistake, right? Why we do that? Because once we say that we have this follows normal distribution, then there is a whole lot of properties that you can use. So what are the properties you can use? 68% of the values are between one standard deviation around the mean. So all those properties you can use, right? So of course you'll make some mistake, but that's what they say. If your sample size is more, the assumption that it follows normal distribution will be more and more correct, which means you will make less and less error. Now this seems more like a normal distribution, right? So you guys can tweak with this, play around, and then see what is happening. Is the theory actually following the slides that we are discussing here? So any question on central limit theorem?
So Mani, just to summarize the understanding, so central limit theorem states that if we take like a sufficient sample size, say 15, and we keep the sample size as 15, but we take it that we draw it for 20 different times, like with different data points, and the average for each sample, it will tend to this follow the normal curve.
Yeah, correct. That's correct.
Okay, yeah. Thank you.
Remember that part, it's more than enough. If someone asks you what is the central limit theorem, you can explain this. That is more than enough in interview. Okay, this is just a theorem actually. Nobody will ask you to prove and doesn't make sense to prove. But if they ask you to prove, then you can do sort of this maybe. But of course that won't happen. So it doesn't make sense to us. But there is a good learning and there is a good advantage of this theorem, right? So once we have enough number of sample size, once we have that, we can slowly approximate these distributions into normal distribution. So the whole statistics around actually revolves around normal distribution. And as I've mentioned, right, so most of the machine learning algorithms, so let's say if you use sklearn, so let's say the packages you use is sklearn, So all the functions, mathematics that they have written code for inside sklearn, let's say you're learning about decision tree or support vector machine or anything, the theory that they write, or let's say they are coming up with a formula, they will come up with the formula with the assumption that the data follows normal distributions, with the assumption that the data follows closely normal distribution. Nothing follows exactly closely, but the data follows closely normal distribution. Okay. Now, when you come to statistics also, when you come to, let's say, interval estimate or point estimate also, there also you'll figure out that I'm assuming that the data follows normal distribution. Of course, it will not follow completely 100%, but it's fine. You'll make some, let's say, 10% or 2% or 3% mistake. So that's fine. But say, by assuming this, you get a lot of formulas that you can use for your analysis in your statistics and machine learning. All the sklearn packages generally assume that your data follows normal distributions, assuming that you will apply these algorithms. Okay. So behind the scenes, normal distribution is always following you, even in real life, even in your what do you call statistics and machine learning. Okay, so I'll just complete these slides. So for example, suppose that the sample is obtained containing a large number of observations, each observation being randomly generated in a way that does not depend on the values of other observations, and the arithmetic mean or the sum, both of them you can see. So arithmetic mean of observed values is computed. If this procedure is performed many times, the central limit theorem says that the distribution of average will closely be approximated to, again they say closely approximate, they also will not say exactly, to normal distribution. A simple example of this is, if one flips a coin many times, the probability of getting a given number of heads, so let me underline this. So if one flips a coin many times, the probability of getting given number of heads in a series of flips will approach normal curve. Okay, so with mean equal to the half of the total number of flips in each series. Okay, we'll see this example, you guys will understand. I think we have already discussed this when I was explaining binomial distribution. Okay, so let me show you in picture. One second. Dice. One second. Dice.
I have a question.
Yeah.
Yeah. So, suppose we have a data set and we are sampling the data sort of times, as you said. Okay. But without following this type of method, we are just doing the classical method. Then the curve maybe or may not be the normal distribution curve, right?
Right. So that's why we do, that's a good question. So in reality, most of the times, I wouldn't say most of the times, but let's say it depends on company, which company you're working. So let's say we're working for a medium or a small startup, then you generally don't sample because the data itself is manageable, right? But if you're working with a big company, let's say PhonePe or Swiggy or let's say Flipkart or Amazon, right? So they get ton of data, right? So every day there is so many data that is coming in. So much amount of data is coming. So no data scientist would directly build a model on all the data, on the complete data. They'll definitely sample the data, right? Now, when they sample, of course, these normality assumptions and all these are not going to perfectly apply. But the good point is these machine learning algorithms are powerful enough to understand that part. Like what I mean by understand is they will be able to capture the pattern in the data, even though your distribution is not completely normal, or you have different types of distributions like normal distribution, bimodal. So what bimodal means is, So sometimes you when you plot the distribution, right? When you plot the histogram, so you will see this one. So that's why I asked anyone has any counter example. So this is a bimodal distribution, right? So this is called bimodal. Okay, so this is a bimodal. Sometimes you will see this one, right? So this we have discussed. So let's say salary. So let's say there will be a skew on the right side, so right skew, right? So let's say sometimes it might not even follow normal distribution. Something like this. This is completely some other distribution. That's completely fine. So you don't have to worry a lot about that. So what happens is there is a step. I don't know today if we have chance or not, but I'll explain you maybe in the next class that what we will do to these types of columns, right? So by doing some transformation, what will happen to these particular columns? So there is a step called normalization. So which is important in machine learning, which we'll do in the next class maybe. So this step will try to convert each column. So let's say this is your column 1, which has bimodal problem. This is column 2, which has right skew problem. This is column 3, which is not even following any distribution. It's not normally distributed, right? So then we will apply normalization at column 1, column 2, and column 3. So this sort of brings these two closer to your normal distribution, right? So as much close as possible to normal distribution. Okay, so my point is basically even if you sample, right? Even if you're working with a column which has some not so perfect normal distribution, that's completely fine. So as long as you normalize that column, you will be good to go, right? So your machine learning algorithms will fairly be powerful enough to understand that part, right? Okay, this distribution is not completely normal. So that part you don't have to worry a lot. But once you work on examples, you will understand this in greater detail. Once you would work on it.
Mani, one thing that in this method means sampling a lot of times. In this method, we are forcefully normalizing the data, right?
No. You're getting confused with CLT and normal life. So CLT is just a theorem. Okay, CLT is just a theorem that you have to keep aside. In real life, I only sample once. Why am I sampling? So two concepts. So CLT has a intermediate step. Intermediate as in there is a between step where sampling is required. Now CLT is using sampling to make a point that the average, when you make an average of different samples, that average value generally follows normal distribution. This is CLT. This is where CLT is. What happens in real life? So real life, I get, let's say 10 GB data. Okay, 10 GB data. And this 10 GB data, I sample once. So let's say I take 500 MB because I cannot work on 10 GB data, right? So this sampling is done here to explain or make a point that the average follows normal distribution. Now from here, from the 500 MB, let's say I have 17 columns. So C1 to C17, right? So what I was explaining is the column 1, column 2, column 3, these will be like this. So some might have bimodal distribution. So this is a bimodal distribution. Some might have right skew. And some might not even follow normal distribution. Something like that. Not like this, but something like that. Okay. In real life, I do not do all this sampling again and again, and I will not do average and all that. Just to explain you or to give you idea what is a CLT. Now, what I do is with the help of CLT, how many rows I have, let's say C1 has, let's say the number of rows I have, is let's say 1 lakh. How many columns I have? 17 columns I have. Now, what assumption I'll make is CLT, with the help of CLT, I can approximately say that this C1, C2, C3, total C17, approximately, right? So approximately follows normal distribution. What it means is, since I have a lot of sample, so let's say 1 lakh values, I will say that this closely represents normal distribution. So that is the point that I will use from CLT. I will not do that sampling again and again. I'll find the mean. All that we will not do. So what we learn from CLT in real life is approximately my column 1, column 2, column 3 will follow normal distribution approximately. Okay, with that assumption, I'll go and build a machine learning model. Now, what happens is, if I do in the vanilla form, meaning that if I don't do normalization, then this machine learning algorithm will perform, let's say 80% of the time, like 80 times out of 100, it is doing well, right? Now, even this machine learning algorithm is having some assumption that I want the data to be normalized. Now, let's say in the approach number 2, I take C1, C2, C3 and normalize these values, right? So I normalize these values. I'll explain in coming classes what is normalization. Then my machine learning algorithm will perform, let's say 84 or 85% of the times. Like it will make 85 correct answers out of 100 times. Okay, so that is what we have to remember as far as we are concerned from machine learning. Now this CLT will be used in theoretical many other statistics. We don't have to worry about that.
Mani, I have one question. As
Yeah.
per my understanding, all the data sampling will be done by the data engineer, and machine learning people will be using that one.
No, no.
As a machine learning engineer, do we also need to do a sampling?
Yeah, of course. You do everything. Data engineer doesn't know anything. We'll only have information where the data is, how to get the data, and how to give you. Sometimes data scientists have to do that job also, depending on the company. The boundaries are very blurred actually nowadays. You have to sometimes also do data engineering also. So let's say
Okay.
there's a big MySQL database, and they'll give you password and login ID, and then they'll ask you remove the customer sales data and then build a model. That's all. That's the problem statement you'll get, and you have 1 week. So all the things you have to figure out. Okay. So the reason that I've pulled this up is, so as the n increases, right? So what it means, so as this n increases, n equal to 1, n equal to 4, n equal to 2, 3, 4, 5, 6, you can see that it converges more and more, and it looks more and more like a normally distributed curve, right? So what is this? This is basically the PMF. What is PMF? Probability mass distribution for the dice example, right? So when you throw the dice n equal to 1, so the probability of each of them falling on, let's say 1, 2, 3, 4, 5, 6, 1 by 6, 1 by 6, 1 by 6. Let's say if you throw the dice, which is n equal to 2, and then what is this bar? This bar is basically the sum value. If you throw the dice, what is the probability that you get 2 is basically 1 by 12. Wait, 1 by 12 or 1 by 36? I think 1 by 36. Okay, let's say if you throw a two dice and the sum value, right? So basically the sum value coming up to, let's say 3 is basically 1, 2, 2, 1, right? So 2 divided by 32. At the same time, the probability of when you throw 2 dice and the summation value is coming up to, let's say, is 34, okay, is also 2 by 36. Okay, so what you have to understand here is, as the n increases, so n equal to 2, n equal to 3, and n equal to 4 here, and n equal to 5, the average, basically what they are finding is the PMF for the PMF, probability mass function for the summation of the dice. So when the dice falls, right? So like this, what is the summation of the values? So summation and average are more or less same, right? So average is basically sum divided by the number. So this also follows. So using this, you can say, Mani, I know that CLT, when n increases, the n increases. So n increases from 2, 3, 4, 5, and 6. So this PMF, the probability mass function, will become more and more and more and more similar to my theoretical understanding, which is the normal distribution. So as you can see here, this is more smoother, right? So this is more smoother. I will get a more smoother curve like this, normal curve here, than here. So let's say here I'll get like this sort of like this, right? So this is, if you make n equal to 6, it will be even more smoother than this, right? So that is what CLT is explaining. So even what it means in theory is, as the n increases, the binomial distribution closely resembles now the PMF for binomial distribution, the probability mass function for binomial distribution will closely resemble your normal distribution. Even this particular, as the n increases in the dice example, when you're working with the sum as the what you're trying to look for, this also closely resembles normal distribution. As we have discussed in many examples in the beginning, once the number of samples, so let's say if I do a problem, right, if I go back here, So if I go back here, so let's say if you remember, if you take the problem statement 1, so the problem statement 1 was salary of, let's say, 10 people in my class, let's say. What is the problem statement 2? The salary of, let's say, 20 people. Okay. What is the problem statement 3? The salary of 50 people. Okay, salary of 50 people. Okay, let's say all the learn by students. Let's say what is problem number 5? Let's say the salary of, let's say, all the people in my company. Let's say 1,000. Right. So what can you understand here? Mani, this will follow normal distribution, but not so smoother. But as the n increases, it will follow more and more and more closely the normal distribution. So same goes with weight, right? So as I collect my sample size more and more and more, the weight will follow normal distribution very, very closely. So this is what CLT is basically. So as the n increases, it follows normal distribution more and more closely. Like all the distributions in nature, more and more closely, they will converge to normal distribution when the value of n increases, right? When the value of sample size increases. Is it clear? So this is what you have to understand from CLT. So CLT is basically two things. If someone explains or asks you, whatever we have discussed in the example that I've shown. And the second thing is, as my sample is increasing with the help of law of large numbers. So there is a law of large numbers. And with the help of CLT, I can see that. So P4 follows normal distribution very closely than P3, right? So the attempt of P3, this follows more smoother normal distribution than this. Okay, so whatever the assumptions I make in normal distribution and come up with the formulas and answers will be more accurate than this part, because the sample size is, let's say, 20 times lesser here. So here it will be not even close. So here it will be some other distribution that we'll discuss in the coming classes. But as your sample size increases, so that is what you have to understand. It follows more and more closely the normal distribution. So is this point clear? So this is more like a theory, but it's an important theory to understand. So that is what.
One doubt.
Yeah.
Which complements which first? I mean, CLT will complement normal distribution.
No, there is no complement. You just say that I know CLT and CLT says this. Complement is this, right? So complement is, let's say you have complement of 60 degrees is 30 degrees. What complement means is this both of them add up to 90. The complement of, let's say, 65 is 25. Right? Husband and wife are complement, husband and wife for a family.
Okay. In other words, if I want to put my question is like CLT at the end of the day, if you put, it will behave as a normal distribution only.
Yeah, CLT, what it says is, as your sample size increases, if you have enough sample size more than 30, you can closely say it follows normal distribution.
And in normal distribution, again, we say that the more my sample or trials area or the frequency, it will come into it, the distribution will follow normal.
The sum of those values will follow normal.
In CLT or in normal? The sum you're dealing.
No, so okay, so there are two parts. So any distribution, any distribution. It could be 1, 2, 3, 4, it could be 5, 6, whatever. When I do a lot of sampling, right? So let's say if I do S1, S2, S3, so on till, let's say, S100, enough samples. The average of this, the mean of this, what is mean of the sample one? So let's say what is my sample size is 10. Okay, how many values I have? Let's say 1000.
Okay.
Okay. The mean 1 of sample 1, the mean 2 of sample 2.
Yeah. M3, M100. So okay.
This follows normal distribution. So this follows.
That follows. Okay.
Now on the other situation, let's say I have column 1. This is machine learning perspective. So this is theory.
Okay.
Theory. Okay. Practically, if you see C1, C2, C3, right? So when you have enough number of samples, so let's say in data set 1, you have, let's say, 100 rows. Let's say 100 rows. And you have another data set 2, which has 10,000 rows.
Okay.
Now what I'm saying is, in D2, the similar column 1 will follow normal distribution in a closer way or in a better fashion,
Than the C1.
than CD1.
C1, no, D1. Okay.
C1 of D1 because there are less samples. The sample size, the number of rows is basically 100 here. There is 10 here. This theory, this is practical. Like this is real life. What we will understand from this. If someone asks you theory, you can explain this. Practically, what you use from this is you can use from this. So as your sample size increases, your machine learning algorithm also will perform better. Now internally, you can save money. The assumption that all these packages have made that it is normal distribution is fulfilling more and more. Now, if you have a data set of 100 rows versus if you have a data set of, let's say, 1 lakh rows, so this will perform slightly better because there is a lot of values. There is a higher chance that the normal distribution, that assumption that they have used will follow better. If you fill these gaps in a better way, it will perform better versus if you come up with a normal distribution like this and you have some missing gaps like this. So this is not a normal distribution actually. It is just a approximate because there is a gap here. Okay.
Got it.
So this is theory, guys. Don't confuse theory. This is practicals. Practicals is as your data set size is increasing, your assumption or your assumption in your machine learning or your whatever the packages that you're using, it follows normal distribution will satisfy more and more and more. Okay, that's why your machine learning algorithm will perform better if you give more data versus less data. Less data, there is a very high chance your ML algorithm will make more mistakes. If you give more data points, it will learn better and it will follow that normal distribution approximately. Sometimes this normal distribution might not be always valid. So there are some techniques that we will show in the class and hands-on that what do we do money. In this case, it is not following normal distribution. Now, if you remember from the beginning of the class, I'm only telling normal distribution. So it is so important. It is that important, right? So, so all the things in nature and statistics and machine learning, it is a good idea for you to guys to have some theoretical understanding and practical understanding. So it is clear proof, right? So whenever you see this one, so whenever you see this also, so this is a dice example, the summation value as the n increases, this also falls closely normal distribution. At the same time, the binomial probability distribution as the n increases, approximating binomial with normal. So as the n increases, the number of trials increases from 30 to 100 to 200, you can figure out if you remember the histogram that we have drawn in the that we drew in the probability classes, it will become more and more and more smoother and closely resemble normal distribution. Okay, so there is some more
question.
Yeah.
How do we define more data?
How do we define more data? Okay, that's a good question. So in statistics, there is a standard. If any data, if you have less than 30 samples, then the assumption of normality won't valid. If you have more than 30 samples, it is called, you can closely approximate normal distribution. The 30 is the checkpoint. But that is sort of gone now because in real life, there is no way that you get anything less than 1,000 nowadays. All the data sets that you get nowadays will be at least 1,000, 10,000. Now we have a problem on the other side. Like past 4 years or 5 years back, you had a problem on this. The problem was the assumption of normality. Let's say you have a data set which has less than 30 rows, then your normality assumptions are not correct. You have to do something else, right? You have to follow some t distribution or something. But nowadays, after let's say 2014 or let's say, let's take it from there, 2014 till 2020. So all the data set that you get is at least 1,000 rows nowadays, right? 1,500. So you can say that normality assumptions is normality distribution assumptions are most of the times valid in most of the cases. It's very rare that you get a data set which is like extremely small like this. Here also you cannot do ML, sort of you approximate these into some statistical behavior. But when you get more than 100 or let's say 1,000 or 500 or 2,000, then you don't have to worry about this normality assumption.
In your project, how much are you usually pick
In
for
my
sampling?
project, usually I work with Somewhere around 1 lakh, 2 lakhs, or somewhere at least 50,000. If I'm talking about company level, then that is too much actually. It is sometimes goes to 2 billion. Sometimes it goes to how much is that? 2 million. 2 million as in 20 lakhs.
For
So
sampling.
yeah.
Mani, I have a confusion. What
Okay.
is the difference between sample size and number of samples? In the case of CLT, do we go for number of samples or the sample size?
Both affect actually. If you experiment this URL, right? So if you experiment with this URL, let's say if my sample size is only 3 and I'm taking 25 draws, so let's see. Sort of follows. So what you have to understand is the sample size is the number of the values that I'm picking. So let's say out of 1,000, sample size is, let's say I'm taking 5 and I'm doing draws. Let's say this is theory again. Let me write it here. This is CLT theory I'm explaining. Okay. Sample size, if I'm drawing, let's say again 3 or let's say 5, then you can clearly see here it won't follow normal distribution. Right, it is this guy is outside and there are gaps, so it will not follow. So let me increase the draws to, let's say 10 or 11, whatever. Now also it's not following. So effectively, in my opinion, as far as I remember, sample size is important actually. If my sample size is more, let's say if it is 13, even though my draws are less, let's say if I draw only 5, 14, let's say 7. Yeah, even that is a problem. So most of the times I think you should have enough draws and enough sample size for it to actually closely follow normal distribution. So let's say if I do 15, yeah, so this is where your this part I don't clearly have an answer, like how after what point of sample size and what point of draws does it actually follow the normal distribution. On the other hand, it doesn't follow. So is that your question?
Yeah, so
Yeah.
we are referring to the sample size means number of samples we take in at one iteration, right?
Correct.
And draws means number of samples we are going to.
How many times you do that? How many times you repeat that experiment?
Okay.
This is theory, guys. It's fine. You don't have to worry a lot, but it has some good applications. That you have to remember the application. This is a theorem. Theorem means like there is x square plus y square equal to 1, then that sort of thing, right? So this is a theorem. So there are some, okay, I think today will be mostly theory.
Just one question. Mani. So you mentioned there's a new problem now, right? So what was that?
The new problem is excess of data, right? So my laptop cannot work on 10 lakhs or 5 lakhs. It takes like 2-3 hours. So the excess problem is that now in that side of the problem, we have more than enough.
Okay, so we need more computation power now. Okay.
We need more computation power and cost.
Like GPUs we need.
Yeah, I wouldn't say GPUs. Yeah, you can say maybe in 2020, yes. Slowly, yes.
Okay.
Okay. So there is some theory, guys. So this is some interesting problems, but it has some good explanation. So this URL, everything is in this PPT. You guys don't have to worry. So these are the properties actually. I've been explaining normal distribution for so long, but Mani, what are the properties, right? So the properties, so we say that data is normally distributed. So what is here? Here it's, so the data can be spread out more on the left. Okay, this is the frequency on the y-axis and these are the buckets or the bins. Okay, let's say if you have 40, 50, 30, whatever values. So you put them according to the bins. Let's say 40 to 50, 50 to 60, 60 to 70. Let's say if you have 61, 62, 63, the frequency is 3. So you have 3 values between 60 and 70. Similarly here, let's say if you have 10, 20, 21, 30, 21, 33, Tanvin. So you have a bucket of 10. Let's say 10 to 20, sorry, 5 actually. 10 to 5, 15, 15 to 20, 20 to 25, 20 to 30. So what they're explaining is on the y-axis, there is a frequency, meaning how many values are in that interval. And they're explaining the data can be distributed in different ways. So it can be distributed more on the left, or it can be distributed more on the right, or it can also be jumbled up, right? So jumbled is also normal, natural. It is quite possible. Okay, but there are many cases where the data tends to be around a central value with no bias left or right. It gets close to, so if you read all the sentences till now, nobody says it's perfectly normal distribution. Everyone says it's approximately normal distribution or closer to normal distribution. So that is where you have to remember, it is all approximation. So statistics is all about approximation. Nobody will give you exact answer. They will say money more or less like with 5% error or 2% error. That's completely fine. So because we are trying to find a bigger picture with just a little bit of data. Okay. So a bell curve, this is like a bell in a temple. A bell curve is a normal distribution, and this is how it generally looks like. Okay. So many things closely follow normal distribution: heights of the people, sizes of things produced by machine, errors in measurements, blood pressure, marks on the test. Okay. We say that data is normally distributed when the mean, median, mode are all equal, symmetry about the center, 50% of the values less than the mean, and 50% of the values greater than the mean. Okay, exactly these numbers won't follow. You might also say that there is 49% left and 51% to the right. Then also we'll say it is closely a normal distribution. Okay. Now
so one thing. So this normal distribution or the bell curve, it is in industry. Is it used to calculate the approximity of the calculation?
Yeah, all of them we take this as a reference point, and we use normal distribution for, I'll explain, like once we do some problems, you'll understand like, what is that, why, how and why we can use this. Okay, let me give you an example. I'll come back to that question. So let me finish some properties. Okay, so the standard deviation is a measure of how spread out numbers are. Okay, if you want to read more, we have discussed the standard deviation of that formula. So what it means is, so these points are very, very important for the concepts that you want to learn in the next classes. So this is your mean. Okay, one standard deviation towards the right, one standard deviation towards the left. Okay, this particular area will cover 68% of the values. Okay, what it means is 68% of the values are within one standard deviation of the mean. Okay, 95% of the values are within two standard deviations of the mean. 99.7% of the values are within 3 standard deviations of the mean. Okay, so we'll see one example. You guys will understand what it means. But I hope you guys remember standard deviation, mean, all those calculations and all that. Okay, so these 3 properties are important. You guys have to remember. So let's say if I ask you 95%, where does it occur? So it is basically money, 2 standard deviations left and 2 standard deviations right. Together it is 95% of the values. Okay, so keep in mind the y-axis is always frequency. It's not the real numbers or the values. Okay, so let's see one example. You guys will understand. So
one standard deviation of the mean is our IQR, right? Or IQR 68%.
IQR is only 50% actually. So IQR is median, by the way. Actually, there is IQR is computed around median, if you remember.
Okay, yeah. But in a normal distribution, mean and median.
In normal distribution, yeah, mean and median are same. So IQR is sort of, how do I explain? IQR is mainly to figure out your box plot and outliers.
Okay.
And in IQR, this box, whatever we have, okay, this contains 50% only. This is 50%.
Okay.
Here it is different. So here from one standard deviation, so one standard deviation and one standard deviation, right? This covers 68 or 69%. 68 or 69. Some books you will see 68, some books you will see 69. Okay, so 68 or 69% of the value. So these three numbers you have to remember, guys, going forward. So 68%, 95%, and 99.7%. So let's do one problem you guys will understand. Assume, so example, 95% of the students at class are between 1.1 meter and 1.7 meters tall. Assuming that this data is normally distributed, can you calculate the mean and standard deviation? Assuming that the normal data is normally distributed. So this is the assumption that they are making. Now in real life, is it completely true? Not really, right? So there will be some mismatch or some error. That's completely fine. But we are able to find the mean and standard deviation by making this assumption. So that is the beauty about this. Now, what is the mean? Mean is basically the center point or halfway, right? So what does 95% mean? 95% means there are 2 standard deviations either side of the mean. So total there are 4 parts, right? So total there are like part number 1 standard deviation, 1 standard deviation, 3, and total 4. Okay, so this value minus this value divided by 4 parts will give me 1 part, which is equal to 1 sigma, or basically 1 standard deviation. Okay, so this is how you can get some different types of problems, but this is all statistics, but statistical problems are something like this. Okay, so it is good to know the standard deviation, because we can say that any value is likely to be within 1 standard deviation. 68 out of 100, any value. Very likely to be within 2 standard deviations, means 95 times out of 100. Almost certainly within 3 standard deviations. Okay, almost certainly between 3 standard deviations. Okay, now this is where your normal distribution will, the theory and all that concepts are present. Okay, now the second concept that you have to learn here is basically called standard scores. Okay, so these are called your Z. Okay, now this is what I was explaining. So Z is basically your standardizing your values. So this is what we will do in machine learning. So generally, let's say if you get 4 columns, so C1, C2, C3, and C4. So let's say C1 is basically your salary. So C1 is basically your salary. Let's say C2 is basically your height. Let's say C3 is your age. Okay, and let's say C4 is basically your weight. Okay, now what we do is generally as a data cleaning or initial step is, so how does salary look like? Let's say salary we saw, right, in the earlier case. Let's say 1 lakh, 2 lakh, then 3 lakh, then let's say 4 lakhs, then let's say 5 lakhs and 6 lakhs. Okay, what about height? Height will be, let's say, whatever, like 170 dot. Remaining values you can imagine. Same with the age. Let's say 30 years. Let's say 31. Let's say 32, 33, 34. Same with the weight. Let's say 50 kg, 50 kg, then again 70 kg. Now this is what your original data frame or data set will look like. Okay, what we do is we convert them into individual Z scores. Okay, we convert each value into individual Z scores. Okay, why we are doing that? We are doing this because this will approximate more closely to your standard normal values. Okay, keep in mind in the notation, I am saying standard normal values. There is a standard now. Okay, this is standard. Till now I was talking about normal distribution. Now I'm talking about standard normal distribution. Okay, so there is a difference between that. So this is a normal distribution. Okay, this is a normal distribution. A standard normal distribution. So a standard normal distribution will look like this. Okay, a standard normal distribution will look like, the mean will always be 0 and the values will always be your Z scores, like let's say 1.5 or 1 or basically -1. This is what we get in data.
Oh, why?
Can you mute? Okay, so this is what we get in the data set. Okay, the data set. What we end up doing is we standardize those values into standardized normal distribution. We convert all the distribution of the values, the normal distribution, to standard normal distribution. Okay. Now by that we will convert these values into your z-scores. So that is a way of converting them into standard normal distribution. So with that, all the values will be between the range of, let's say, -3 +3. Okay, you will convert these values, you'll convert these values, you'll convert these values, all of them into standard.
Why the mean is 0 here?
Why the mean is 0? Yeah, I'll show you the formula, then you'll understand. So the formula for converting any value into standard normal distribution is, so let's say you have, this is the formula. The formula is x minus mu divided by sigma. Okay, so this is your mean, this is your mean, and this is your standard deviation. This is your standard deviation. Okay, so let's say these are the values, right? So let's say, how will I convert them into standard normal distribution? So what is the mean here? So the mean value is basically 10, 10. So the mean is basically 10, 10. What is the standard deviation?
Twenty.
Let's say if I get a value which is 970, okay, if I have a value 970, how will it convert? So it will convert to x minus mu. So 970 minus 10, 10, 10, 10 divided by sigma, which is 20. So if you do that, the answer is -2. Okay, so this 970 will become -2. So this is just a way of standardizing the normal curve. Now what about 10, 10? So since 10, 10 is basically same as mean, so this value, the mean, will always end up becoming 0. Okay, what about the value which is 1050? So the 1050 is basically 1050 minus 10, 10 divided by 20. So the answer is +2. Okay, so +2. So these values are called your z-scores. So these values are called your z-scores. So let's say if I have a value which is 965, so 965 will become somewhere around -2 or little bit -2.1 or something like that. Okay, so let me explain this. What is the use of this? How will we use this? So
the data set should be normally distributed.
No, you normalize each column according to its own column, so that you bring those values as close as possible to normal distribution.
No, the green curve I can see that is normally distributed.
Okay.
But our real-time data will not be like that.
Yeah, let it be. So what I'm saying is real-time data, of course. So this is all theory. So in no real life you will get this data actually. Out of 100 times you get 1. So what about 99 times money? Of course, 99 times we need some way of going forward, right? We need some assumptions or some way of doing things. So that is what we say. So out of these 99 also, we will approximate it to normal distribution. We'll assume that. So if you see here, the question also says, assume that, where is that? Assume that the data is normally distributed, right? So that assumption they are making, right? So similarly, out of these 99 times also, we'll assume that it is normally distributed. So even though it doesn't look so symmetric, so let's say it looks like somewhat like this also, we'll do standard normal distribution. So we'll convert this approximate. So let me make it approximate normal distribution. So approximately normal distribution into approximately standard normal distribution. Is it clear? So in real life, of course, you will not get this symmetric curve.
So is it, suppose it is not symmetric, it is skewed, okay. Then after normalizing, it will provide the bell curve always?
It will provide closely better than this original values. It will, because since your values are going from any range, so let's say before you can have any range of values, and since you're converting and normalizing them, it will go into between -3 to +3, right? So this is -3 to +3. So what you're trying to do is you're trying to bound these values. So let's say in this particular problem, okay, in this particular problem, now what is the range of values? The range of values are between The range of values are between 940 to, let's say 940 to 1070 or 1080, right? This is the range of values, right? Now, since it could be skewed, left skewed, right skewed, whatever, but I'm trying to bring it down to a scale, right? I'm trying to bring it down to a scale which is between minus, let's say 3.5 to plus 3.5. Plus 3.5. Okay. Similarly, what is the range for your salary? So the salary was ranging between 1 lakh to, let's say, 15 lakhs. But what I'm doing is even this same thing, I'm trying to bring it down to this particular scale, right? What about your weight? Weight was also ranging from, let's say, 165 centimeters to, let's say, 180 centimeters, right? So any range of columns that I have, let's say C1, C2, C3 that I've described, they can have any range. What I will do for machine learning algorithm is I will bring all of these into a standardized distribution. So standardized Z scores. Now these will closely follow normal distribution better. Now, nowhere I said exactly perfectly. I'm always saying better and closer and approximately. Now these values, whatever I have normalized Z scores, will follow normal distribution better. So the keyword is better than these values, right? So than these values. So let's say there is some skewness, or there are some measures to, there are some ways of handling skewness that we will discuss. How do we handle skewness? But in general, the reason that we convert all of these columns into this standardized form is it will be easier for your machine learning or algorithm or any other package to work on a similar scale of data, right? So all of the scale is basically between -3 and -3.5. In real life, nowhere you will see this symmetry, and this is like actually the very exceptional case. But why we are learning this is with the help of this and making the assumption that it follows normal distribution, we are able to go forward and do all our calculations and normalization. Once we
so in summary, so the reason why we are going forward with the standard normal distribution. So first thing is we can convert the different scale to a single scale.
Correct.
And also the standard normal distribution follows very closely with the normal distribution pattern, right?
Correct. So we never say it follows perfect normal distribution. Of course, your mean median mode will not reside. So that's the summary actually. In summary, we can say these two statements.
Okay.
Did I answer your question, whoever asked before?
Yeah.
In real life, nothing follows normal distribution, by the way. But this is some means you need, right? So somewhere you have to stand, right? So somewhere you have to take some support. So that support is given by this normal distribution and all the properties that it comes with. So for example, so if you see here, so a survey of daily travel time had these results in minutes. The mean is 38.8 minutes and the standard deviation is 11.4 minutes. Okay. Convert these values into Z scores. Okay. So all you have to do is X minus mu divided by sigma. Okay. And when you plot it graphically, it will look something like this. Okay. So the formula for finding the Z score is called X minus mu divided by sigma. Okay. Now, yeah, this is a good question actually. Let me show you the question. So the question is, why standardization? It has two benefits. All of them bring to the same scale. And I don't know if you guys remember, but in our college, they used to follow this. So it can help us make decisions about data. This is not related to machine learning. This is more like a statistics or a business analyst type of requirement. Example, professor, let's say Mani is marking a test. Okay. Here are the students' results out of 60 points. Most students, if you see the marks, what are the marks? So the marks are students got 20, 15, 26, 32, 18, 28, 35, 14, 26, and 22 and 17. So this is for 60 marks out of 60 marks. Now, what can you comment about the test? What can you infer or what can you say? Looking at the marks and the total number. So what do you guys understand? Like this is the marks that people got in the class and this is the total number of marks you can get.
They got less than 50% of the total points.
Right. So which is basically the exam is hard, right? The exam is difficult, right? This is what we can say. Okay. Now let's say in normal case, the cutoff marks are 30. That you guys agree, right? So most of the times out of 60 marks, they keep a cutoff which is 50%, which is 30. Now, if I go with this logic, of keeping the cutoff as 30, now how many people I have to fail? Technically, all of them, except these 32 and 35, all the other students I have to fail. Correct? Now, is there a better way of failing students?
Don't give them marks.
What?
We can take the
We can take what?
percentile.
Percentile. Okay. Closely, right? So that is what we are trying to do here. So you are trying to standardize, right? So the test must be really hard. So the professor decides to standardize all the scores and only fail people one standard deviation below the mean. Okay. So let's say what is the mean score? Mean of the marks is 23. The standard deviation is 6.6. When you convert these values, into Z scores, so these are Z scores. These are not your original scores of the values. So what is the mean? Mean is 23. What is the standard deviation? 6.6. Okay. So this is minus 0.1.21, then 0.45, 1.36, and all that. Now, if you see here, now only 2 students fail. The ones lower than one standard, one standard deviation. Okay, what are those values? So those guys are basically 15 and 14. So out of those, instead of before I was failing all the class, almost all of the class. Now by standardizing these values with the help of mean, standard deviation, and Z scores, I can take a better call. I can take a better statistical call by failing only these 2 guys, so which is 15 and 14. Okay. So this is another use case or another way of why standardizing helps. Okay. Now this is so this is all I had for normal distribution and CLT. Okay. Now there was one more thing actually.
Mani, can you please ping this link in the WhatsApp chat, please?
Yeah, this is already in your
Okay.
So all the links are here. You guys, there are even more links if you want to read more. This link is also good. If you want to learn more about this, like if you want to dig deeper and you have a lot of time to understand more better and better, all the URLs that I have given here are here. Okay. For example, the CN theory, standard normal distribution, the DICE example, and all of them. Okay. Now you guys want to do hands-on. Actually, there are only 20 minutes. I think it might take some time. Okay, let's do hands-on. So let's open your Jupyter notebook. Can you guys open your Jupyter notebook? And yeah, yesterday I forgot actually some concept. So in case of time series, guys, so in case of if your column is time series, the way you split your test and train is in this manner. So let's say this is 1st January, 2nd January, 3rd January, 4th January, okay, and then let's say 31st January. Okay, the way you create test and train in case of time series data, the way you split is you keep first 25 days as training. So first 25 days as training. Okay, first 25 days as training, and the remaining 5 days or 6 days test. So if you guys remember, right, we did randomly all that. In case of time series, it won't be random because your curve will look like this. So what you do is you split this part and try to learn here, and your model will try to predict this part. So let's say it will do something like this, right? So it is learning. So it has learned till here, and it is predicting on the test data set. You can say that Mani, this is more or less fine. So that's fine. So I can take this model. But whereas in your, if you remember the earlier example, the test train, so this is random actually. So this works randomly like this. So here we do it in this fashion. So in case of time series, keep in mind your train and test is sequential, like the first some portion, let's say 10, 20, 30 days, sorry, 25 days or whatever, 26 days or whatever. And the remaining part will be your test. So your model will learn how the pattern is going on and predict the pattern in the remaining black color curve. Okay, so that thing I forgot yesterday actually. Is it clear, guys? So in case of time series, there is a difference. How do you make the test to train split? Okay, in case of normal times, you do normally whatever we have discussed. But in case of test to train, you do it in a different manner. Okay.
So Mani, this is the data set we have to use or the banking data set, the one which we were using yesterday?
Oh, 1 second, just I'm thinking actually. Can someone ping the bank data set here one more time? Yeah, I think I have it. I think no. No, can you ping again? I don't have it. Yeah, let's keep that loaded and all that. So let's see how we can do normalizing. Okay, so let me rename this. No. These are like the basic things you can do like all the time so that you get practice. So this is just nothing new. So let's see one column. So let's say if we take df of age, these are the values. Okay, so let's say yeah, so this is what we have discussed, right? So we want to convert them into z-score. So x minus mu by sigma. Right? So you can do this. Okay, and then what is the code? You guys can do it along with me when I'm doing. You don't have to wait.
Hi, Mani.
Yeah.
My data set is looking different after DF.
Why? Different as in? Should look like this.
No, it's not looking in that.
Did you use separate?
The first part, DF, after DF, everything has moved towards right hand side.
Yeah, you have not separator, right?
Okay.
Yeah.
Okay, that command. Okay.
The same data set we are doing 3 days. Separator is important, guys. You need to learn from it. So if you don't use this part, this is what you'll get. This is wrong.
Yeah, the same.
You have to use separator because your separator is not comma here. That's why you have to do this. Okay, so if you run into that issues, next time if you run into that same issue, you can use that so that you can, so instead of actually copying this, if you run into errors is where you will learn maximum. So that's a good, so use the separator. 1 second here, I'm trying to figure out. It is asking me to take 2-dimensional data. Key error, age duration. So the way you can find the columns is like this. Default. Spelling mistake is there. Duration. Okay.
If the
Mani,
data
can you
is in
give
the
us an
form of
overview
list,
what we are trying to do here?
So I'm just trying to convert all of these values. So if you see df of age, I want to convert them into Z scores actually.
Okay, understood.
Yeah, that is what I'm trying to do. Just thinking what is the correct syntax. I'm getting some error. Someone was saying something. What is that?
it is in the form of list. The way they are passed the data.
Yeah, that's what I'm wondering. Like, what is the correct way of? It's a list of this standard scalar pandas. Scalar dot fit df of age.
Can we first try fit?
Yeah, fit also won't work again.
Mani, there's a spelling mistake in duration.
Oh yeah.
TION.
That's working. Okay, so the way you select these columns is like this. So let's say if I don't know, for some reason that's not allowing me to do for one column, but anyhow, let's do for 2 columns. Duration.
It's allowing for one column as well.
Working, huh? Is it working?
Yes.
Okay. Yeah, it's working. Okay, cool, good. So let's say if I do age. By the way, guys, so this is the correct way of accessing 2 columns in one shot. So there is one more list inside. So I want to select age and duration. So my original age and duration are the values 30, 33, 35, 30, 59, whatever. I'm trying to convert them into Z scores. So if you see here, so what I'm doing is I'm using sklearn standard scaler. If you go to the documentation of standard scaler, what it is doing is z equal to x minus mu by s, where mu is mean and s is sigma, all that. So I'm trying to convert these both of these columns into their z scores. So we have just whatever we have discussed till now. So we can do it in one command. So the first is basically import this package from sklearn.preprocessing, import standard scalar, and then create an object out of it. So basically you have to do scalar equal to standard scalar like this. And then you can do scalar dot fit transform. So let's say if you want to do for one column age, let's say if you want to do for multiple columns like this duration. Okay, so you can see, right, the value 30 is converted into minus 1.056. The 30, why is 33 converted to minus 0.77? Yeah, 33 is converted to minus 0.77. Is it correct?
Yeah, Mani, I guess the mean is 39. So this will come under left side, 30.
1 second. So this is an array.
Money, mostly it is an increasing value. That's why this one value is increasing.
Okay, what about
minus 0.077 is greater than minus 1.05, right? So that's why this one it is that is the pattern it is following. If you can see 33 and then you go 57, or there is, I don't know what is that mistake about.
So the mean is 41.
Yeah, let's do this.
But is it matching the both of them? Are they matching?
Yeah, that's what I'm looking at actually. Or maybe they are doing something. 1 second.
Can we try and get the mean and deviation for that? Yeah, we'll see, and then one value we can try it. What it's given.
Yeah, mean is 41 and standard deviation is 10.57 for age column.
What does it mean?
Mean is 41.17 and standard deviation is 10.57.
Standard deviation is 10.57.
Yes.
So let's say if I do x minus mu by sigma, which is x minus mu divided by sigma, 10 point.
Money, I guess it is matching over there. It is matching the last 3 rows. If you see the last 3 rows, which is 57, 28, and 44, it's matching with those. Like 57 is taken as 1.49, 28 is taken as minus 1.24, and 44 is taken as 0.26. Those are the 3 values. Bottom and the top one is this one, 30, 33, and 35.
Okay. You're saying it's matching.
Yeah, so this is also matching, right? Mani, what you have calculated, that is matching with the first value.
Yeah. I think we don't have to question sklearn, but anyhow, so I just wanted to make sure. I was confused for some time, but yeah. So you guys can see, right, how we can convert the values, which is 30, 33, 33, whatever, 35, 59 into this particular fashion, which is basically your minus 3 to plus 3, right? So these are your Z scores. So this when you do this, so what you end up with is basically the Z scores. So you can do this in one shot for all of them. So let's say duration, right? So duration is, if you see the minimum and maximum of duration, so let's say df of duration. So duration is in another scale only altogether. So duration is somewhere at 79, 220, 185, 195. But by doing this standard scalar, you are bringing all of those values into the same range, which is minus 3 to plus 3. Okay. Of course, you will remove NN values, but for now you can ignore that.
I have one question, Mani.
Yeah.
So these 2 columns, they are anyway related for the, I mean, will they be relative value or will these be independent, these scores for these 2 columns?
Relative as in?
Relative as in all the values for this age and duration will come to a common point, and then all the values will be relative to other.
No, I'm not understanding. So what this particular process of doing this is, so you have 2 columns, right? So C1, C2, let's say you have another column C3, right? So this had a scale or a range of, let's say, starting from, let's say 30 and going all the way till 58. So this is the range or the window at which the values are ranging. Now, if you take C2, which is duration, which is starting at, let's say 79 and is going all the way till 300, right? Now, of course, you can give this in this format to your machine learning algorithm. But what happens is if you convert all of them into a common scale, right? So the common scale, so all of them have a common scale. Now, keep in mind this 79 you are doing with respect to this column only. You're not, there is no, all the normalization is being done according to your individual columns. I'm not mixing values. I'm not taking any global minimum or all something like that.
Oh,
not doing
got
it. So this is applying on this, converting according to this. This is applying on this, converting according to this. Okay. The only reason that I'm doing is here you can see this scale is 30 to 50, smaller one. Here it is 79 to 300, very large one. Let's say if you have 1 lakh to 2 lakhs, it is even large. But once you bring them, all of them into a common scale, which is running from -3 to +3. Okay, it will be easier for your ML algorithm, and all those normal distribution benefits will come into play. Okay.
Okay.
Mani, one question. Whenever we are displaying this age or duration, so we are giving two lists inside, right? Along with DF1. That is a normal syntax, like using two lists.
The normal way of selecting two lists, two columns at one shot.
Okay.
You guys can experiment with all this. Actually. You guys can see what happens if it is. Right, so this is not normal, right? So this is not normal, perfectly normal, I would say. So this is more or less, you can say, a right skewed graph, so somewhat like this. So this is nowhere normal. This is not normal. But we can say that, so if you want to do, there are 3 minutes. So if you want to do this, you guys can do this as an exercise. So what is the percentage of values? So let's say 68% of values are between 1 standard deviation left and 1 standard deviation right. Okay. Now in above age column, what is that percentage? Can you guys do this? If you guys get time, maybe for 15-20 minutes, can you do this exercise? So let me make it here. I'll upload so that you guys can remember. So what is the normal distribution? Say 68% of the values are between 1 standard deviation left and 1 standard deviation right around mean. Correct. Now, since we see this is the graph that it is looking like, can you guys tell me how much percentage of the values are between 1 standard deviation left and 1 standard deviation right towards the mean? Is it 65? Is it 60? Is it like 72? How much is it away from 68, the standard value? Can you guys do this as an exercise? I'll upload this Jupyter notebook so that you guys have the problem statement.
Could you please explain the question again?
Question is, if you take the hypothetical, the theory part, what we learned was in a nice symmetric normal distribution. The theory, what we learned in theory is there is 68% of the values. There is 68% of the value between, this is your mean. There is 1 standard deviation left and 1 standard deviation right. So the values between this range, let's say this value is, let's say 16 and your mean is, let's say 25. What is the standard deviation? Let's say 9. So 9, 34. So what it means is if you have any normal distribution, a perfectly normal distribution, 68% of the values. So 68% of the values. So total you have, let's say 100 values. Total values you have as 100. Total is 100. Let's say Total is 100 values. Among these 100, 68 values will be between the range 16 and 34. Okay, that is what your theory says. Now this is practicals. So let's say this is the real life data set. Now how many values do you have here? You have 4,000 something, 500, whatever, 4,000, 5,073. Now my question is, calculate the mean. Okay, calculate the standard deviation of this. You can use NumPy or Pandas, whatever is fine. Let's say the mean value comes to, let's say 36, and standard deviation comes up to, let's say 8. Okay, now what is the range here? So the range is basically 1 standard deviation minus, which is basically 28, I think, and 1 standard deviation plus, which is 44. Okay, what is your mean? Mean is 36. Mean is 36. Now my question is, how much percentage of the values, how much percentage of this, how much percentage of this is question mark? So how much percentage of this is between this range? So 28 and 44. Of course, these values I'm making up. You have to do it programmatically. So what is the value you get here? So here you got, out of 100, you got exactly 68 values are between 16 and 34. Since this is a perfectly normal distribution. My question here is, this is, I'm saying approximately normal. Can you guys come up with the number? What is this particular question mark here? Is the question clear?
Yes, it's clear now.
Yeah, don't do by hand, do it with code. I mean, like hand, as in like, don't do, try to come up, how do you use NumPy, I would say. Use NumPy package. Okay, do it as an exercise. You guys will get some more clarity, some more errors, some more problems. So that you guys will get a hang of normal distribution. What is the standard deviation? One, left, right, all that. Okay, guys, I'll close the class here today. Any other questions? I'll stick around for another 5 minutes. Meanwhile, I'll upload these notebooks.
Yeah, Mani Purnima here. So, yeah, I'm trying to draw that histogram for age column, but as my Pandas is older version, so I have imported Matplotlib, but how to give that option for histogram? I'm able to plot this box plot. Can you just tell me the code for that?
Can you mute? So let's say if I don't know, right? So let's say I want to figure out plot histogram. You can do these 3 commands. It should be same.
Okay, Mani, I'll try. Thank you.
Yeah.
And Mani, about that fit and transform method. So what is it transforming and what's it? Data is fitting into that, is it? It's because we use a lot, right? Is that everywhere fit?
Yeah, fit and transform is 2 things in one shot. Fit means first what it does is fit will figure out what is the mean standard deviation. Transform means it will convert all these 4,500 values into z-scores. So fit and transform in one shot means first it will figure out mean, median, all that, and transform means it will convert all of these values into a new Pandas data frame or new this output result. You can read more about this here actually. If you go to the documentation, so there are many functions. So fit, compute the mean and standard deviation to be used for later scaling. Fit to the data, then transform it. So you can go to the documentation and you can figure out what is the exact, what is happening. Okay.
Sure, thanks. Yeah.
Yeah, I just calculated it came around 58.
Why did you calculate so fast, man? Should give chance to everyone. I don't think they will do now. But anyhow, yeah, you can see, right? It's very way off from the standard. So it is 68, right? So we'll make a big mistake actually. We'll make some reasonable amount of mistake by approximating it to normal distribution. But let them also do. Tomorrow we'll discuss.
Okay. Okay.
But the question isn't the how many values are there in that 4,500, right?
Yeah. How much percentage? I'm asking percentage. Always percentage. Percentage. Okay, guys, then I'll close the class here today.
Mani, one thing. So on the other day I tried to upgrade the pandas, but it ran for more than 3 to 4 hours, but it was still in that loop only. So do I need to uninstall Anaconda and install again? Okay, but I won't lose my Python notebooks, right? If I do uninstalling and installing.
The Python notebooks will be stored in a specific location wherever you say it.
Okay, yeah. Yeah, then I'll uninstall and install Anaconda. Thanks.
Mani?
Yeah.
Please upload the link for Cayley-Hamilton theorem you have provided, no? Please upload it in the classroom.
Yeah, it is already done.
Okay. So, thank you.
Yeah. Okay, I'll close the class here today, guys.
Okay, thank you.
Yeah.
Thanks.
Yeah.
Thank you.